and change in coordinates with y. That means how has x changed from 0 to 1, how has y changed from 0 to 1. Now if you look at the new coordinates of x, let's say this is a vector, the new coordinates of x here will be equal to, let me draw it like this, right? So this part is going to be cos theta and this is sin theta, right? This part, because for the new frame here, because this is theta, this frame also has rotated by theta here, this angle will also be theta. So this is going to be, minus sin theta, and this part, this whole part will be cos. So I can write this as x, the coordinates of x, cos theta, sin theta, coordinates of y, okay. So this is the coordinates of x. This matrix 2 by 2, R 2 by 2, 2 cross 2, is a frame rotation matrix, which means that it will provide a relation between frame 0, I'll write frames as F0 to frame 1. Okay. This is a rotation by the angle theta. So these are the new coordinates of x and new coordinates of y. How does this help me? If I want to find the new coordinates of P after the frame has been rotated, P1, which is in the new frame, will be equal to R01 times P. I can multiply this rotation matrix with P to find the new coordinates of P. Alright, so this will be new coordinates after rotation. So this is with respect to frame F1. This is the original coordinates. With respect to frame 0. Okay, so we can translate the coordinates based on the rotation. Now, when I'm rotating this frame, we mentioned one thing, that translations are along an axis, rotations are always about an axis. So to produce this rotation, about which axis have I rotated? The rotation is about which axis? Z axis, right? It's always a perpendicular axis. So if I want to extend this into 3 dimensions instead of 2D, if I want to extend the same thing into 3 dimensions, you write it like this. This is obviously a rotation about Z because it's an axis perpendicular to this. We are rotating it like this. So R, Z, theta. That means a rotation about Z axis by an angle theta will be equal to, we'll write the same thing, cos theta minus sin theta, cos theta. Z remains the same. Z, nothing changes along Z. This axis is the same, you're only changing the other 2 axes. So along the Z vector, we'll have 0, 0, 1. Okay, this is a rotation about Z by an angle theta. This is a So this is how the same thing will extend it to a 3-dimensional case. This is rotations in 3D. Let me write it here. So if I have x, x remains the same, so x will be like this. This is the rotation about the x-axis by an angle theta. And finally, the rotation about y. So if you want y, then this is y is going to be 0, 0, 0.
Why change?
I'm sorry?
Should we constant minus in
Which
sin
one?
theta?
For x or y?
Yeah, y.
For y.
Everything changed then.
Y is this axis, right? If you write x,
Y, z. But what I mean is,
y.
we started cos theta at x and z,
Yeah.
but we started minus sin theta at the y.
Okay, so every time when you change from x to y to z, it shifts and moves down 1. Okay, so if this will shift and will move down 1, so then you will have cos theta sin theta here, because this will go up.
Oh,
Got it?
yeah.
Or you can derive this instead of, if this is a, let's say you want to do this, right? Then this will be x, z naught, this is y, and then you can derive the same thing.
Okay.
Okay? Excuse me. You'll have to remember these three matrices. Really, if you want to solve any of the problems that we have, otherwise it will be hard to solve them if you don't remember these. So this R3 by 3 is an interesting matrix. It's a 3 by 3 rotational matrix. Call it a 3 cross 3 rotation matrix. I'll explain this once you finish copying.
Professor, for the y coordinates, can you explain the shifting a little bit?
For the y one?
Yeah, from x to y.
Okay, so, see, when you rotate about a particular axis, nothing changes about that axis because that axis is remaining constant. So if I have three axes, right, x, y, and z, when I rotate the frames, this axis is remaining the same. Or if I rotate about this axis, the coordinates about this axis remains the same. So for example, when I'm doing about z, only x and y will change, right? Nothing changes along z. So we write z as 1 because it multiplies by itself and you get the same coordinates along z. So z is constant. When you go to x, I'm rotating about x. Okay, this is rx comma theta, or ry comma theta is known as axis angle notation. Which means that it will tell you what axis you are rotating by and by what angle you are rotating, right? About which axis and what. So in this case, x is constant. Here, y is constant. Okay. So there is no change in coordinates about y. So diagonally or across, we'll write this. So when I move from here, so basically it moves like this and it shifts down by 1. So when it shifts down, this will fold down.
Yes.
Okay. Or you can derive this once again. So
if that happens, then the sin theta, how come the sin theta is in the bottom? It should be in the top, right? On the rightmost corner of the y theta. Rightmost column of the y theta.
give me 1 second. You're probably right. Let me check. Give me 1 second. So x is, z is this. Let me check this. Let me check 1 second. Let me make sure. X, we're good. Y, and Y is when we shift it. So when we shift this down, obviously this will be cos theta. So this will be sin theta, and this will be sin theta. Minus. And this will be here, because this moves down here. This will come down. Minus sin theta, cos theta, minus sin theta, cos theta. Fine. All right. So this will be y, x. Let me confirm z. Yeah, you're good. Okay. So please make this change. I'm sorry, I had that the other way around. So this will tell you what angle axis notation is. Now there is one thing that we'll discuss a little later, which is every rotation does not have to be about a standard axis, which is it always need not be around z, y, or x. It can be about any arbitrary axis k. So you can have this as k theta, in which case you'll have to derive your own system to represent the rotation. In this case, we have standard rotations. So this, you can write it in terms of these standard rotations. This is about a rotation about an arbitrary axis. Okay, this is an arbitrary axis, k. So, now
How do we come up with the arbitrary axis rotation?
we'll talk about that once we do a few examples. We'll do an arbitrary axis a little later. Okay, so when you have the R3, 3 matrix, it belongs to a special group of matrices which is known as SO3. SO3 is a special orthogonal group of matrices. Okay, special orthogonal group of 3 by 3. 3 tells you the order, which is a 3 by 3 square matrix, and this is a special orthogonal group. The reason we classify it like this because it has a certain set of properties. The first one is R transpose is equal to R inverse. So if you want to transpose this matrix R 3 by 3, it will be equal to, or if you want to invert it, it will be equal to its transpose. Okay. So the first thing is the transpose of the matrix is equal to, is the same as its inverse. Second thing is all the rows slash columns are orthogonal. What do you mean by orthogonal? What is orthogonality?
Eight sides.
Orthogonal means perpendicular. Okay, so if you take the dot product of two rows or two columns, you'll get 0. Okay, all the columns or rows are unit vectors. Okay, all the rows and columns are unit vectors. And finally, the determinant of R 3 by 3 is 1. Okay, so it's a unit matrix. The determinant is 1, and this is a property that is very handy because if you want to rotate it, let's say I have a frame rotation like this by an angle theta, So if I can write frame 1 to frame 0 to 1 as R, frame 1 to frame 0 will be equal to R transpose. I don't have to calculate that all over again because it's the inverse rotation. So I can go backward and forward by just taking the transpose of that matrix. So which is very convenient, and that is a property of the special orthogonal group. There are other properties, we'll talk about that later. So for now, we'll stick to these. Once again, make sure you have an idea about these three matrices, because until we go to a 4x4 matrix, we'll stick to the properties of this to help us do a few simple problems. Okay, let's take an example of consecutive rotations. Now it's easy for you to understand here. For example, let's say that I have a point, consider a point P 3, 2 with respect to a frame F0. Okay. Now the frame is rotated about the z-axis by an angle of, let's say, 60 degrees. Right? Find the new coordinates of the So, you have a frame and you have a point P here. Okay, this is the point P with respect to frame F0. This is the frame F0, X0, and Y0. Now we rotate this frame by 60 degrees. So you have rotated it like this. This angle is 60 degrees, let's say. Now this frame is X1, Y1, and F1. About the z-axis. So z-axis is here perpendicular to the board. Now you want to find what are the coordinates of this new point. So P1 will be, let's call that as P dash or P1 with respect to frame 1. That will be equal to the rotation matrix, because first thing is you have to write a rotation matrix from frame 0 to frame 1. This is R01, right? R01 is nothing but a rotation about the z-axis by an angle of 60 degrees, because you're rotating about z-axis by an angle of 60 degrees. So this ties up, or it explains the relation between the two frames. So now we can use this to write the coordinates of P1 or P dash. P dash will be equal to we'll have to include, because this is a 3 by 3, I'll have to include one more, otherwise it won't multiply. So let's say this is 2, okay, or minus 2, right? So this will be, if it was a 2 by 2 case, that would make sense to have a 2D point, so this will be equal to cos 60 minus sin 60, right? And you get your new coordinates of this. Conversely, if I gave you the new coordinates and I asked you to find the old coordinates, then you'll transpose this matrix. Okay? You'll transpose this matrix and then find out the old coordinates. We'll do a few problems about this. Let me just introduce you to a concept, and then so that it leads us to the next class. And then we'll come back, when we come back, we'll do a lot of problems with rotations and everything. This is just a simple example, but obviously I'll give you more examples to solve. let's say I have two rotations, or what we call is a case of consecutive rotations. Okay. So let's consider a case where I have the first rotation of theta about x-axis. Okay. Let me say the axis. And let's say an angle of alpha about x-axis. Okay, this is my first rotation and second rotation. So let's take the first axis here. All right. So now I'm rotating by an angle of theta about the z-axis. So the positive direction of rotation is, if you point your thumb towards the axis, this is my positive direction of rotation. This is by the angle theta. So I'm rotating about this angle. So when I do this, I'll have x1, y1. So this is moved by theta, and this will move by theta. This is fair enough, right? So I'm going, this is my frame 1. So this will be frame 0 to frame 1, and this will be frame 1 to frame 2, right? Okay, so alpha about the x-axis. We have two x-axes. Which x-axis should I rotate by? x1 or x0? x1. Why not x0?
It's already rotated on the z, along the z-axis after.
Okay, so if I rotate about x1, so let's do x1. So this is x1, I rotated about x1 by an angle of alpha, right? So this is my second rotation. When I rotate it about alpha, x1 will remain the same, or this will be z0 and z1, because z1 and both are the same, it does not change. When I do this, x1 and x2 will be here, they don't change. But the other two axes will change. So this, when I move it like this will be y2, this will be z2, right? Okay, so that will be y2 and z2. Let me do the other case, where I'm not rotating by exactly the same thing, but I'll rotate by the other axis, which is the other x-axis. So here we have your x0, y0, z0, okay? My first rotation was about theta, about this axis. This is theta, right? So this axis does not change, so this will also be z1. It remains where it is. Now we have the first axis, which is x1, y1. Okay. Last time we rotated about this x-axis. Let me rotate about this. Which is by an angle alpha. So when I rotate about this, because I'm rotating about this axis, the current axis is x1, y1, z1. So all three will rotate when I rotate about this. So this will go, because I'm rotating it like this, x2, y2, z. So as you can see, there are two ways to rotate this. So unless it is specified, you cannot tell which rotation is required here. The first one is obvious, because there is only one z-axis. But the next ones are not obvious. So always when you have a consecutive set of rotations, you will have two options here. It will either say rotation about the current axis or fixed axis. Okay? This one is a current axis rotation, because you rotated about x1, not about 0. So in this case, the second rotation, rotation 2, is alpha about fixed x-axis. Okay? The first one is the same, which is theta about z-axis, because there is only one z-axis, all right? In the beginning, there is only one z-axis. Once you rotate, you have one or more axes. In that case, you'll have to specify which rotation it is. Are these two rotations the same? No, right? So if you're tracking a point P with this set of rotations or this set of rotations, the coordinates will be different. So the way we represent R02, because you're moving from frame 0 to frame 2, in this case, R02 will be equal to the first rotation, which is R01, or which is Z about an angle theta, so this is Z theta. And then you have current axis, which will be X alpha. Okay, this is a current axis rotation. In the case of a fixed axis rotation, same thing, R02 here will be equal to, you write the first rotation, which is Z theta, but instead of post multiplying, you'll pre-multiply this. This will be X comma alpha. This is a fixed axis rotation. Okay, since matrix multiplication is not commutative, which is AB is not equal to BA, these two will not be the same. Okay, in this case you are post multiplying, here you are pre-multiplying. So whenever you have a fixed axis rotation, you multiply before. If you have a current axis rotation, you multiply after the post rotation. Okay. So current axis is here, post multiplication. Okay, a fixed axis is pre-multiplication. Obviously, you have to bear in mind whether it mentions the rotation as a current axis or a fixed axis rotation. If it's a fixed axis rotation, it will be like that.
It's so confusing.
So let me give you an example of consecutive rotations. Let's say we have three sets of rotations. First one is a rotation about the x-axis by an angle theta. Two, the rotation about the current y-axis by an angle theta. Three, a rotation about the fixed z-axis by an angle. Okay. So let's write the composite rotation. Write the composite rotation matrix. Okay. So you have three rotations. We need to write. This is a composite one. That was a simple current or a simple fixed. In this case, R3 by 3, the rotation matrix will be equal to, we'll start with the first one, right? X theta. So axis angle notation, this is X, theta. This is my first rotation. Okay. Now we have a current y-axis by angle beta. So should I multiply here or here?
After.
After, exactly after. So this will be y beta. This will be my second rotation. And because it is fixed, I'll have to pre-multiply the last one. Z angle. This is my third rotation. Okay. So starting with the first one, if you move to the right, starting with your first rotation, this is one, this will be all current axis. And if you move to this direction, this will be your fixed axis rotations. Okay? So if you move to your left, it's all fixed axis rotations. So if you want to...
Never mind.
Huh? You're all right. Okay, so let's try to visualize this. It's important to understand how the frames rotate so that when you solve problems, you have a visual interpretation at the same time while you're solving a problem. So first is x angle theta. Again, I'm going to point my thumb towards the axis direction, so this will be an axis theta. Okay. Since this is a same axis, my x1, because I'm rotating about this, my x1 will also be here. Okay. Because this, when I rotate about an axis, that particular axis remains fixed. So when I do this, this will be y naught.
Come on.
X naught, followed by current y-axis. Next, I'm rotating by the current y-axis by an angle theta. So this is the rotation of theta about the current y-axis. So I'll have, this will be y1. Okay, so this will take me here. All right, and finally, rotation about the fixed z-axis. Fixed z-axis is z naught. So when I rotate about z naught by an angle of phi, so I'm rotating like this. Okay, so when I do this, z2, x2, and y2, they'll all move in this direction. So I'll have z2 will become z3,